very happy to have Yaniel Cabrera from TAMU. Is this another place? Anyway, he's going to tell us about RG flows between the CMOD and theory models of the defects.
Hi, welcome everybody, and thank you guys for giving me the opportunity to talk about one of the projects I'm working on with our friend Yaniel. We should have this out very soon. So, about 9 years ago, people started studying topological defects. It's like two-dimensional one objects that sit in your theory. In our case, we'll be talking in 2 dimensions, so it'll be just lines that separate 2 theories. They come with a binary operation called fission, where this picture can be made into this picture by bringing the 2 defects arbitrarily close together until you get just one defect. They're topological in the sense that your correlators are not affected. You have 2 field insertions. Then the values of correlators are not affected as you deform this correlator around your wall sheet. They're very powerful tools because if you have a symmetry in your action of the theory, you can represent that using defects. You can talk about RG flows like we'll see today using defects. You can talk about dualities between different theories, a T-duality using defects. Also, for example, we have built defects that enforce T-duality. And in general, you can map one theory to another by moving your defect across. For example, this is one observable in your theory 1. There's another one over here, theory 2. As you deform this picture and you bring the defect across in this way, theory 2. You obtain an operator now, a field that lives in your older theory across a defect. In our case, we'll see an example how we can use these objects to study the RG flow of these models. And more importantly, we'll see how we can use it to tackle the question of RG flows in the boundary. When we have a theory with the boundary, the question of what happens to the degrees of freedom on your boundary as you have an RG flow. So you have an RG flow in the bulk. So you have some deformation that leads to an RG flow. As you bring this flow to the boundary, what happens here is now very well understood, either in condensed matter or in string theory. In our case, we'll do exactly the same thing. We'll have a perturbation in the bulk. And we let it flow to the UV. So we have the theory going to the UV here, but we still have the remaining theory in the IR outside the subset. And then with this, we construct a defect sitting between the 2 theories. And we'll show that when we let this defect go to the boundary, so we let epsilon go to 0, the fusion here between this defect, call it D, and the boundary, call it B, denoted by a star, gives the right boundary in the UV. That is, UV B in the IR is mapped to B correctly in the UV. In our case, our theories will be these non-compact orbitals. Can people see as I write across all the boards? I seem not to be very efficient with space. Okay, so we'll describe this supersymmetric orbifold using a chiral superfield. Let's denote it X. Yeah.
So what happened here? So you moved the defect over, and then but you had to pinch it off. Sorry, in this middle port.
Oh,
over
right.
Phi 1.
Right. As we come across, the defect actually wraps around. So you deform it, you deform it, deform it, you deform it, keep deforming until you pinch it off exactly, and you obtain this picture. Yeah. Then you let this go to 0. You shrink this to 0, and you obtain now an operator using the other theory.
So defects are only defined up to homotopy? Is it just,
Homotopy?
because, I mean, is it to say that these two are the same in some sense, or what is, or like moving, can you just move defects around as you like?
They're the same in the sense that your observables will not be affected. Your correlator functions won't be accepted. Won't be affected.
Okay.
Basically, the boundary, you're saying something like the boundary conditions on the defects between your two topological field theories already defines for you a map from the local operators of one theory
Correct.
to the local operators of the other.
Correct.
And that's what that picture shows you somehow.
That's right. That's right. And in the case we're going to talk about, we'll have a language for what these operators are. Yeah. Okay, so we're going to parameterize the space by a chiral field X with action with the lambda Ginsburg model for. This will be our action.
Can you say more about the supersymmetry? This is 2, 2 in 2 dimensions. And
That's right. So these are chiral fields in n equals 2, 2. And we expand this out, we get the bosonic term. Oops, okay. Is it the same bottle from before? Oh, it's out.
I'm just pressing these over here.
Yeah, no, I think that's better.
Technology.
If we expand this out and we do the integrals over the fermionic variables, we obtain your action. Something like this.
Do you mean x bar?
Oh yeah, yeah.
Otherwise it'd be 0, right?
Yeah. Okay, so this is the D term. So going to the general lambda Ginsburg model, they're written as S is an action of a D term plus an F term. This is the D term.
Actually, I'm sorry, wait.
Yeah.
I think I didn't understand. So if x is complex,
That's right.
then you should have a bunch of like the phi at the phi bar and a bunch of different.
Yeah.
Bar there, or are you just being schematic?
No, this is schematic. That's right. Yeah, complex value. That's right. Yeah. This is the D term. This is the kinetic terms. And in general, we have an F term. In here, the F term will be 0, which I will pedantically write it. The F term, in general, F term is a real part of this integral, where W is a holomorphic function of the chiral field. Now, this action is supersymmetric by construction under the 2, 2 theory. But upon the introduction of a boundary, like we care about in our case, the 2, 2 is broken down to about half, it's actually half of that. So our integrals here, the space integrals will be done over sigma, where sigma is the upper half plane. So we have to introduce some boundary conditions on the fermionic degrees of freedom that live on the boundary. So, and in that case for us, it's going to be this. This is B-type supersymmetry, and then also same thing for the bars. On this sigma. All right, so we can have something like B-type, this is called B-type boundary conditions, or we can have A-type, where we mix the bars with the non-bars. Now, we want to vary this action on the type of supersymmetry that preserve the B-type boundary conditions. Okay. The general B-type boundary conditions are preserved by this variation. And we won't use it explicitly, so I won't write it completely. There are a Q and a Q bar, which are linear combinations, diagonal linear combinations of the 4 generators that you have in the 2,2 theory. Okay. So we don't need to know explicitly what they are. I just leave it like that. And we demand to have that delta B of the action is 0. When we do this and we integrate, we obtain boundary contributions from both the D term, the chiral, the kinetic term, and the F term coming here on the boundary. Now we can add a boundary term to the action that cancels out the contribution from SD. So delta B can be set to 0 by adding an appropriately built boundary term using just bulk fields. So this is taken care of. Okay, but that cannot be done for the F term. There is not such a thing that we can do, not such a term. For the very delta B as F, we obtain this. I'll write it. Where T is the variable on the boundary. So now we have the question of getting rid of this term here, so we can keep the symmetry.
D theta or D squared?
Say it again.
Do you mean D theta or D squared?
D squared theta. No. Just no. So now we have only 2 thetas left on the boundary, and here this is only a function of half of that. Yeah. So a kinetic term on the boundary will have 2 thetas. Yeah. An F term from the boundary will only have 1 theta. Okay, so the question is, what can we do to kill this contribution so that we can keep supersymmetry? For that, we introduce new boundary degrees of freedom. So we introduce a whole set of new fields that reside just here on the boundary of our space.
Have you said something about Zn already? Because you didn't, maybe I didn't hear it, but you.
No.
Zn says something about W, right?
No. Okay, so Cn in general, so we have the potential will be something like this for us. So we'll have Cn here will be, this n will be the D here. Yeah, in general. We're going to be considering W0, but it's still the action of this group. Yeah, it's still less invariant, the D term.
Sorry.
Yeah.
I'm confused by that. So, like, in the action, you have the F term
Mhm.
0, right?
So that's right. The action describing this theory is this one here, where the superpotential is set to 0. But I'm describing the theory for any general superpotential right now.
Sure. So F term and F bar, they don't need to be 0. Yeah, they have some variation like this.
Say that again.
I mean, so generally, like, you consider F and F bar not equal to 0, right?
Yeah, that's right. That's right. In this case, we're considering where the F terms are non-zero. We're having superpotentials of this form.
Right. Okay. So this delta is this delta is for delta B, like B type, right?
Correct.
So just from curiosity, can you write down the delta for A type?
For A type, I don't. It's so we will have. So the Q and the Q bar for A type are different.
Right.
And then A is something like this, I believe. Something like this. Yeah, in this case, these Q's are actually like Q plus Q minus, and similar for the bar. Yeah, where these are the generators of the 2.02 theory. Okay? Right, so as I said, we want to introduce now new fields entirely that live in the boundary. And this will be these pi's, pi i's and pi I bars. So we introduce on the sigma. These are fermionic non-chiral superfields. And the whole purpose is going to be to give us like B-type supersymmetry. I will just give you what the necessary requirements for this to happen without entering in all the details. I'll give you what are the things needed for these objects to give us back B-type supersymmetry. They're going to have a kinetic term.
What's the range of I?
The range of I. 1 to R. That's free. Yeah. So the non-chiral D is some function that depends on the boundary restriction of the bulk fields. And this is the D now from 2,2, but the D that is just a translation of the Q in the B-type supersymmetry. And they have an F term on the boundary. That is like this. Again, this is just the F term, so it's only one variable, 1 theta, and it couples to some functions. And these JIs are small potentials that are also functions of the boundary restriction of the bulk fields.
E's also have an I.
That's right. Yeah. Yeah. Thanks. That's just the F term. It also has a kinetic term, which is just pi bar.
With measure d theta bar.
Say that again?
With the measure d theta bar.
D theta bar, correct. Yeah.
How many new degrees of freedom are in capital pi I? Is it just like a scalar, little pi?
No, so it's no, it has so little pi I will be a fermionic, but it also has a linear term in theta.
How much of that, so does this relation determine those things in terms of the bulk fields entirely? Is it good, like the way, it looks like capital pi has no new degrees of freedom because it's given in terms of the bulk fields.
Yeah, the construction of pi I. No, for example, this will be just part of the highest term in pi, the one in in 2 thetas. This is not saying anything about the lower components of
If
pi.
E is 0, you're saying it's chiral, but it's not, right? In
Mhm.
general, so you're fixing the chiral part to be something that is already given as original data.
Correct.
But you still have the theta part, phi, which is pi, which is a new boson that lives on the.
Correct. And also the little is lowest component, most lowest component also.
Thank you.
Yeah. Now, okay, now with that information, we have that delta V SF in the bulk plus SF on the boundary is 0 if this is true. If W factorizes this way over the superpotentials J and E. Okay, so given that, this will be true. Again, I'm not giving you what the variations of the pi's are. That's also determined. That's also has to be written down to obtain this. Just in the interest of time, I'll give you just what's necessary. Now, in the bulk, as I wrote over there, we have Q bar, and they satisfy Q bar is something like 2I D plus D minus, and Q. So let's put B so we don't get confused with the bulk with the full 2,2 theory. So this is B for B type supersymmetry. This is Yaniel potent also. So, yep. Okay.
Annoying question, but X's are bulk fields. Am I supposed to think of this thing on the boundary as being pulled back, or?
Which thing? The
Well,
J's?
X's are bulks, right? So
That's
are
right.
J's pulling them back, or?
Well, X is in the bulk, and XD is the value of this on the boundary.
Oh, that's D. I thought it was.
Oh, yeah.
I was thinking. I thought it was index. Okay.
My bad.
I see.
My bad.
How many fields pi I do you have?
That's up to you. You can have. That's right. That's right.
What if I set them to 0?
If you set them all to 0.
You have to have at least one.
No, if you set them all to 0, you're not restoring B-type supersymmetry.
You're tapping.
Well, what's the minimum number then? to have
1.
symmetry?
Oh, 1.
Then why do we put an index I on it?
Oh, because we'll see that it'll be useful to work over a set of them larger than R sometimes.
Larger than R, what's R?
Sorry, larger than 1.
Larger than 1.
Yeah.
Okay.
Yeah.
All right.
That's right.
Okay.
So in the bond, we have this BRC operator Q, defined used as QB, which labels the physical fields. They are the ones that are in the kernel of the BRC operator. Same thing happens in the boundary. As we introduce these new fields, pi's, we obtain a Q that lives on the boundary. And that Q, using the variation which are now writing on the pi's and the equations of motion coming from their action, can be written in this way. Q on the boundary can be written as the sum over the j's times the pi's plus the e's, the potential e's, plus the pi bars. Now, this Q partial, if we square it, we get W times the density. So we can use this Q as a BRC operator on the boundary. If we act with Q on boundary operators using commutators, so for example, two of them will be Q commutator A, commutator A. This will be 0 using this here.
And there are no contributions from the XXOP because everything's homomorphic. Is that how it works?
Say that again.
What you just computed was the commutator between pi and pi bar, right?
Yeah,
You just
here.
erased it now, yeah. Right? That gives you,
Yeah,
if you
X
compute j
is
squared,
homomorphic.
yeah, you're getting the pi bar cross term is 1, and then
Mhm.
you're getting the homomorphic.
Correct.
The swoop thing together. But then you don't have to worry about x contractions because everything's homomorphic.
X, what do you mean by
Well,
X?
J and E are both functions of x, and ordinarily you should compute the Poisson brackets for those two, right? But maybe I think you don't get contributions from those because you would need an x and an x bar.
I didn't think about that, but maybe that's the case. Yeah.
But there's
But in the, just using the pupil algebra and the fact that when the two non-bars or 2 bars is 0, yeah, we'll do
It's
this.
the same for x though, right? The bar with bar, sorry, unbar with unbar gives 0 for x.
Bar.
But those are x deltas, right? So once you put them on the boundary, you're identifying theta with theta bars. So they won't be, would they still be holomorphic on the boundaries?
What's x?
So these are not functions of x, they're a function of x delta.
Yeah, yeah. That's fine. Oh, you're worried about like contact?
On the boundary, you're identifying theta and theta bar.
Well, we probably shouldn't stop him on this, but the W is somehow a bulk guy, right? Or
Yeah,
that thing is a bulk guy, even though you're writing it as pullbacks. So there's something going on there, but yeah. I think
Right.
that-
This is all happening on the boundary. And so the physical fields on the boundary will fall in the cohomology of this guy here. Okay, so let's do one more step to get to the matrix factorization where we want to be, and that is we can choose a representation of this algebra here. Yeah,
That
go ahead.
was an important statement you just made. So now you're gonna think of q squared on the locus where W vanishes, or what? Why are you saying now
No,
cohomology? Because you need things to square to zero.
Here we're squaring to 0 already.
Wow. This
So-
is W evaluated on A, right?
W evaluated and A. No. This is W. This is exactly just the signal potential X. This is the identity. This is the identity on the space of operators with a coefficient, which is this polynomial.
Right, but don't you need the polynomial to vanish in order to?
Are you saying one commutes with everything?
Yeah, that's right here.
W is just a scalar.
W is a scalar for this.
If you use Jacobi, okay, then the commutator vanishes. Okay.
Yeah,
Okay.
that's right.
That's weird, isn't it?
Yeah.
Okay.
Okay, so we can choose a representation for this algebra here. In that case, one can see that we can write this guy here, this Q, in this way. Some P1, some P0. Where depending on the size of your set of pi's here is the size of your representation. And hence the size of these matrices and now matrices. So that's why choosing different pi's here will give you different lengths in the set of pi's, will give you different representations that you can, so you have different sizes for these matrices here. Such that P0, P1 is what? It's gonna be, as with W, X, times identity in whatever size of the vector space you're acting on. So we've gone from talking about boundary conditions, boundary data necessary to have B-type supersymmetry, all the way down to this factorization of physical potential in terms of not all the polynomials, but matrices. The entries in these matrices are polynomials in the chiral superfields. This is called a matrix factorization. Matrix factorization. Is it visible around this board? Okay. So in general, a matrix factorization over two spaces, so we have a capital P0 and a capital P1. These are going to be modules over some ring. So you have some ring. In every case, the ring will always be the space of polynomial on the chiral rings. And you have two maps, little P1 and little P0. We call this P, such that little P0 times little P1 is the identity on big P0 times W, and little P1, little P0 is identity on P1 times W. And these are modules, over the ring that we care about. So for us, this is always going to be the ring, will always look like this, and this will always be a direct sum of these spaces. So for example, if it's rank K, this would be CX, K copies of this. The rank of the matrix factorization is defined as just the rank of the little maps going between the two spaces. Right. So we have gone from cataloging what are the boundary data in our space. We have gone from there to talk about it in terms of matrix factorizations.
Or do you call it matrix factorization?
Because it's a factorization of a polynomial, but the factorizing maps are matrices.
What was K, where'd you get the rank again?
The rank is, I mean, this can be written for arbitrary rank.
P is vector space, right?
P is a vector space. More generally, in this case, we talk about polynomials, so we call it the R module, which is like a little bit more general vector space.
Right, I mean, all around just over a field of vector spaces, but whatever. Right, so, but I mean, the K, what is
Right,
the
because
K?
yeah, we'll see once we're not able to divide most times, so that's why.
I'm just asking what you wrote everything I understand
Yeah.
except for the ring complex ring generated by X direct sum K times. That direct sum K times part,
Yeah.
I missed that. What is
Oh,
that?
this is, so for us, usually, always P0 and P1 will be as R modules isomorphic to one another, and they will be isomorphic to here. And this will be our rank.
And that K is the number of little pi's you have.
That K, exactly.
And here, when you've written Q as a matrix, that's the matrix representation with respect to the basis of the little pi's.
Correct, correct.
Okay.
Yeah.
And you're saying the blocks are the same size.
That's right. Okay, so what do we have? We know how we talk about B. We know how we talk about B now. But we have defects too, right? Defects. So how do we talk about defects? Where we have now one LG sitting up here with some superpotential 1, which is a holomorphic function of some collection of chiral fields X, and an LG2 with some superpotential W2, which is a holomorphic function of a collection of chiral fields Y. How do we talk about this? Well, it's exactly the same description as here. It will be exactly the same description as star, except for the fact that the W there, which is just one superpotential for a boundary condition, will be the difference W1 of X minus W2 of Y. Where this is W1 and W2. So if we go through the same sum and dance, as before, we try to have B supersymmetry across this defect, we'll see that we get to the same point, except that now we're factorizing the difference of the two superpotentials.
And those are evaluated at the defect locus, right? Or do you define it over the full block?
No, once we're in matrix factorization, it's just a polynomial. I mean, this evaluated just, if it's a taking value on the here you can change your variables to just be. They don't have to be. We're not talking about chiral fields here anymore. Just the variables.
Oh, right. So you're just setting up some abstract
Yeah,
factorization.
that's right.
But this came presumably from demanding some SUSY advantage, right?
Correct. Which is, yeah, indeed, in that case, when we're talking about the action, this was not at the boundary or the defect.
Okay.
That's right.
I think I don't understand the answer. So the question is basically, what does Y mean in Landau-Ginzburg 1?
In Landau, in here?
Yeah. What does Y mean
Wait,
in
you
the
mean
first
X?
one?
You mean
No.
X?
What does X mean in 2, and what does Y mean in 1?
He never
No.
wrote this.
Huh?
He never
I
wrote
think
this.
he wants to have that on the boundary.
Yeah, this is only on the boundary.
On D or?
No,
Yeah,
this
on
is-
the defect, sorry, on the defect.
Right. That's right.
Yeah.
That's right.
But he's alluding to a theory in the upper half plane that has a super potential called W of X and Y.
I'm going to. I have
Oh, okay.
right now. I will.
Okay.
I haven't, and I will allude to that theory just so that I don't have to show you to obtain that, but tell you that it's a natural thing to obtain. And as in the preview, we saw that if we have an LG here and an LG2 here with W1 a function of x and W2 a function of y, we saw that this is equivalent to a theory where we have the trivial theory here, that is just a boundary. When I mean boundary, it means like no information flows across. The identity here and LG1 tensor LG2 with the left and right degrees of freedom interchanging LG2. And if you just do this, forget about match factorization, you just do this here, this step here, the folding trick, you see this is an LG with W equals W1 minus X minus W2 Y, with that same sign there. So indeed, when we factorize the defect, we are factorizing the same picture as before, except with this potential. Okay, so now what do we have? We have a description for the boundary of a theory, these LG theories, and a description for the defects between two such theories. What is the next thing to look at? Well, the fusion. We say that defects have this rule where two defects, U1, U2, can be fused together to obtain some new D3, which is the fusion of U1 and U2. All right, in this language, how do we write that? Okay, well, that is done via something called the tensor product of metric factorizations. And it's lengthy and it's tedious to look at it, so I won't write it, even though it's very important. But it's very formal and it's very big to write because we're taking tensors of the different spaces in each of the two different metric factorizations, and we add them up together, and then do the same thing for the other ones, and take different tensors in different ways with the maps between the two metric factorizations. So I won't write it, but the thing is that we don't use that. When we do that, when we have two, say, let's go P, two metric factorizations, say P and Q, 0 and P1. And I want to say Q. Q0 and Q1. And we take the tensor product of these metric factorizations. To obtain some Q prime, which is Q0 prime and Q1 prime with two little maps, Q1 prime and Q0 prime. For example, Q0 prime looks like something like this, like P0 tensor Q1 direct sum over P1 tensor Q0, where the tensors are taken over the polynomials in the chiral fields that live in the middle theory. So this is a picture. We have theory 1 here with variables y, x, sorry, the middle theory with fields y, and the other theory across the defect with variables z. When we squeeze this out, this tensor is defined over the polynomials in the middle chiral fields. But the same way, when we talk about a defect across W with x and W with y, here these spaces here are taken as C, X, Y modulus. Okay? And these spaces here will be taken as C, Y, what? Z modulus, right? Okay. Now we have to interpret these spaces here as C, CX what? Z, right, modulus. Yet, when you do the formal tensor, you still have the Y's hanging around. That means you start with something that are two matrix factorizations of finite rank over the respective rings, but yet you end up with something that, due to this main degrees of freedom, is of infinite rank. because it's like an axis for every y to the k power. That's a k, the k axis that you have as a generator to build on your ring. So this is very bad. You start with two like rank 1 objects, and you end up with something that's infinite rank. Okay, so this is why we don't use this. Instead, there's this very long theorem, which is very long to prove and difficult, and we just use as our workhorse. And I just stated for you when you write it. It says that if you start with two matrix factorizations of finite rank, their tensor product is equivalent to a matrix factorization also of finite rank plus an infinite sum of trivial matrix factorizations. And by trivial matrix factorizations we mean where P1 is 1, P0 is W of rank 1. These are non-physical, we get rid of them, and we keep just what is of finite rank. Okay. Now, how do we do that? Okay, that's the workhorse that we use. And for that, we associate to every matrix factorization P this space, co-kernel of P1. This is the co-kernel of the P1 map, which is P0, the target of this space, modding out by the image of P1. Now, even so that is when we take the tensor product of these two objects and we obtain this Q prime, we want to identify what is this space, co-kernel of Q1 prime. Now, this is still very difficult. So, this is yet another theorem which we use. And that says that this space here, co-kernel of Q1 prime, is isomorphic to this space, the co-kernel. So this all sounds very abstract, but I'll give you an example of M, where M is this space. M goes from Q1 prime to P0 tensor Q0. Not only that, but doing this space, the way we work with it, we're able to peel off what is the finite rank part of Q1 of the tensor product. Right, so we want to look at this. We have two defects, we fuse them, and that's going to give us a new matrix factorization. We can identify that by working out what this space is. We work out what this space is, we're able to identify what the Q1 prime, which is a fusion of these two, is. So now this will be the tool to work with. And so we have boundaries. We have a matrix factorization description for them. We have defects, and we have a matrix factorization description for them. And we have something called fusion, and we have a matrix factorization description for them by working out what some space looks like. So let's just work out one example. Let's look at this defect between y, x equals xd. W2 of y equals 0. And just let them see. So this is a boundary, this is a defect. The language applies even when you have a superpotential to be 0. If you have the potential to be 0, you already have supersymmetry, right? But you can still do the same process of introducing boundary fields and still obtain maps, matrices that will, when you multiply them, you get 0. Yeah.
I just realized I don't know what the line B with identity on B.
Yeah,
What's
this
identity mean?
is my notation for boundary. It means that
Yes.
here, you know, we don't have the theory here.
What was the identity?
Identity, the trivial theory. Literally like a box, it's like a hard wall. And this is
The identity of RG flow or something.
Oh no,
What was the
that's
identity of?
bad. just trivial theory.
Okay.
Yeah, that is bad notation.
Okay, so that the other one in the middle could have been like free y, like there's a y bar kinetic term and it has,
Correct.
but there's no superpotential, and the
Correct.
last one doesn't even have a.
Correct,
Okay.
that's right, that's right. So, I mean, this is not a theory here, it's just a boundary condition at defect. Right, this is just the upper half plane, this is the upper half plane. Okay, let's fuse this guy. When we fuse this guy, we should have W equals xt, and just trivial, right, just the upper half plane. So let's write Pn, this is going to be Cx, y, and Cxy, with maps P1 equals xPn, and P0 equals xd minus n. Right? So this is factorizing what? This is factorizing W1 minus W2. So it's this defect here. Okay, and this n is just a label to like know that I have this xn here. That's just a label. And for the boundary, we can write this very simple matrix factorization. So these are very simple cases just to get a handle of things. Where we have ym is P1, and P0 should be what? These are rank 1 objects, polynomials. I'm factorizing the superpotential P0. Yeah, that's right. Okay, so we want to work out what is co-pair of M. Well, this is going to be P0 tensor Q0 mudding out by, oh yeah, so I told you the spaces that go in between, but I didn't tell you what the M was. What is it? Okay. It's P1, little P1, times identity Q0 minus identity from P1. Identity from P0, sorry, tensor P1. So we're going to mod out by P1 here and by Q1 here. Okay, so what is P0, Q0? Is Cx, y. And what is P1? P1 is x to the n. And P and Q.
Oh, sorry,
Q's. Yeah. Okay. That will make notation easier. And y to the n. But we want to look at this, as we said, as a modulo over Cx. That is, we're going to take the y's as generators. Okay, so that is right. This is going to be yi. I is a non-zero integer. Okay, so a set of yi, I is a non-zero integer. Yi is just y to the ith power. Okay, and this is my set of generators, my set of axes. I'm going to generate this by multiplying with elements of this ring. That's that notation for that. And I'm modding out by these two conditions, xn and ym. Well, this condition here is telling me that I cannot have any powers of m above m, of y above m. All right, so now these I are in 0, m minus 1. So now, and this space here, by the claim that we have, is isomorphic to Croker of Q1 prime. So that is, we have Cx, how many copies of this? M copy, that's right. And then, so this is Q0 prime, and Q capital 1, Q1 prime is the same thing again, M copies of this. And then we have two maps going between them. One of them.
Why are you not just factoring out the x to the n too? I mean, you could have done the same thing with C with the generator x, right? So you would have just said it's a polynomials of degree, y degree at most n minus 1, n minus 1. Right?
Wait, say that again?
Why can't you just say all this whole space is just all powers of x and y all mixed up together?
Yeah.
Where
Yeah.
you have to keep the power of each individual x below n and each individual y below n.
That is true.
Why are you still keeping this quotient structure?
This
You're quotient
quotient
out by
structure-
y, but you're keeping the x.
Oh, this quotient structure, because I'm saying that this space here that we just computed
Yeah.
is isomorphic to this space here. And this space here is going to be Q0 prime modding out by the image of some map which is Q1 prime. So I'm picking out what this map is, for example. And this case is just, it's obvious, it's just the identity on these spaces times x to the n times identity and n by m identity. And again, I'm factorizing now what? When I bring this guy down, I'm factorizing x to the d. So I need to have here what? X to the d minus n. So, okay, again, we have description for boundaries and for defects, and now we have a description of how to work when we bring them, when we fuse them. We know how to obtain what is a metric factorization that corresponds to the tensor product of two metric factorizations. Right, so now we can turn to RG flow defects. What's the time? Right. So time is scarce, but I had to give you just look at the tools that we use. The language is a little bit different. So far, we've been working just with the LG structure, right? We haven't mentioned nothing about the symmetry group that we're acting. We can act on these matrix factorizations.
Isn't this whole factorizing out by your co-kernel m? Isn't that exactly the symmetries?
No, this is just coming just from.
But this is a gauge redundancy, and you're going to talk about actual symmetries in a moment?
This is just coming from a representation of this operator when you square it is 0. It's just coming from there. So the talk has been basically just of C, not mod C and yet. And so I just tell you what is the new layer that comes on top of this without dwelling too much on it. For example, let's use the same. Let's use this guy here. Actually, we actually care about potential being 0. So let's use a very simple case here. In that case, Q, which is Cx x to the n 0. In this case, we have, this is just boundary now. Yeah, just a boundary. Let's consider the boundary. In this case, we're going to have ZD acting here. In this case, the metric factorization has to be equivariant under ZD. That is, if you have a symmetry group, you have to have that the ring structure on your modules have to be, what's the word? Compatible with the action of the symmetry. So that when you act in an element on, say, so the X, this is the generator, this is an element of the ring action generator, you have a symmetry element. You act on this has to be P X. So the symmetry acts on your element of the ring and also on your generator. So that's what it means to be, what's the word I just used? Compatible, right.
Oh.
And also, we have to require that if you act in this space here with a symmetry, and then you send it this way, that would be the same thing as sending it this way, and then I here with the symmetry. In our case, this is the group, so we can label simply the E-reps. The L, we can put the E-rep L on this space. And in this case, this commutation between the maps and the action of the group, then this has to be E-rep M plus L. This will let you see that if you act here, send it this way, it's the same thing as send it this way, and then you act here. In general, if it's a defect, then it has to be equivariant under CD mod CD prime. So the symmetry group will be the one that takes into account both LG symmetries.
That's weird. So your W for the W of X and Y is not a homogeneous polynomial. W of X is homogeneous to degree D, W of Y homogeneous to degree D
That's right.
prime.
Yeah.
W of X and Y is not a homogeneous.
Yeah, but this guy would only act on the X, this guy would only act on the Y's. All right, so the thing is that using this information, we can build some defects, some matrix factorizations, which we label PMN. And they're lengthy. The maps are lengthy.
Does this mean that the
Yeah.
theory on the boundary, or the defect cannot be an LG theory?
Well, the action that we're setting on the boundary, it's the same one as the action of LGs. It has a.
Yeah, except the superpotential is not homogeneous.
Oh, wait, hold
Same
on.
degree.
Yeah, no, sorry, yeah, that's right. Yeah, I guess. So we can, I won't give you the defects now because just writing what the modules are, the piece of compute once is long. I give you the fusion rule between these defects, which we claim are the RG flow defects and the boundary conditions. So let me give you the labels for them at least. Okay. It's M, N. These are the labels for them. Where M is in CD. Yeah. N is a D tuple. D prime tuple. Such that the sum of the ends equals 8. And it's enough to work just with, okay, so we wrote here these guys, we call these guys M, L. L belongs to the E-rep CD, and this M here is this power here. It's enough just to show the 1 with N is 1. So PM and refuse that, so we have boundaries here, we have defect here, we have CD here, we have C, D prime here, and the superpotential is 0. So it's 0 on both sides. Okay, but we still have symmetry groups. With the boundaries, which we label by Q, M, this is the symmetry label, the E-rep label, and then we said if you take this power to be 1, the rest can be reconstructed from here. It's 0 if M is not in some set. And is Q is a different label, A, which is an implicit function of all the labels that we have at hand, but also keeping the same, it doesn't raise the power otherwise. And L, okay, I will write it down. All right, so quickly, very quickly, we can compare this with the actual RG flow. All right, so let's compare it. Let's compare with RG flow. between C D prime and C D. Right, for that we look at the chiral ring. The chiral ring of the theory is all the chiral fields that you have in your theory with a multiplication, because it's still chiral. In this case, C mod CD has a chiral ring which is generated over some x. I won't give you what it is, and some y. Generated over these two guys, modding out by x to the d equals y. Okay. Now, the action that we wrote initially, S, which is just the f term, if we deform this to S prime is S plus some complex constants, J, and the C squared, the theta squared, this X and powers of that, J. This condition here is deformed to this. Y equals X to the D plus J equals 1, D minus 1. Okay, so this is during the RG flow, we have that. And just do 3 more minutes. We can consider that condition there as a polynomial. We can consider that by taking y this way, going from C to C. Furthermore, we can consider this as a branch cover of the complex plane. So for example, we have y equals x to the 5th. We can consider this as a 5-shaded cover of C. It's a branch cover because at any critical point of such a polynomial, say a critical point of order n, we're going to have n plus 1 sheets meeting at that point. So at x is 0, this happens here. They meet, then they go the other way. This is at x, 0. So what we do here is this. We consider this cover, and then we compactify the top. When we compactify, okay, before we compactify the top, we take a path going from the critical value, which is the value of this point, to infinity. When we do that, what happens at the top? We get 5 such paths in this case, right? We compactify this. The picture, the compactified picture of this, compactify, looks like this. Now, if it's deformed, say instead of y to the 5th, x to the 5th, we have something like lambda x to the 3. This picture will look like 22. It will look something like this, where this is one critical point, x at 0, and this is another critical point, which is x1 something, some power of lambda. Lambda is a coupling constant. This is during the RG flow. This graph has some properties, so it's not arbitrary. You cannot make this in a different way. If we send this to the IR, we have this picture. If we send this to the UV, we obtain, in this case, we obtain this picture. The UV, this lambda goes to infinity, and it drags all this path with it. Right, and just 2 more lines. I'll do it over here. such a thing, we can do a graphical representation of all these QAs, of all of these QMs. This M is in ZD. So there is start here, and we have so S0, S1, and then all the way to Sn minus 1. The way this operator acts here is by sending a bunch of them to 0, and the ones that send to 0 are the ones that are not in this set. We can have such a graphical operation here, some operator, we send some labels here, S1, S2, to 0, the ones that have these labels. Okay, so if it's this picture, we can build, this is for x to the 5th. The fact is that we can choose, appropriately choose these labels, M, and all these N's with these restrictions, such that this set here, which I didn't write explicitly, when we put that set into here, so the complement is here, we killed exactly, we can obtain this picture, for example, 3. So we can reproduce those. That action that we see on the RG flow by looking at the branch covers of the chiral ring structure, we can reproduce that using this graphical representation of our RG flow defects. Okay, and that's all.
Thank you. Questions? All right. Well, since it's a little over, let's thank him again and ask questions offline. Very nice. So it's very fast, but I understand.
Yeah, it's introducing the language first. Sessions.
Who was the one originally responsible for the first part of your story? That you guys or something?
No, this is how the inspiration of Brunner and Rodenkamp.
Oh, yeah, I know Daniel Rodenkamp.
They are the ones who introduce matrix factorizations to talk about boundaries and defects in London Gizmo models. And that was the first paper. The second paper actually applied that to talk about the flow of the minimal models by going to the LG language, building defects there, and checking the RG flow of these guys. And these defects are not too far from what they have.
A question that I didn't want to interrupt yet again. So in this RG flow from ZD to ZD prime, should I think of that picture with the defect being either all the way down at the boundary or all the way up at infinity? Or is that not right?
No.
Can I push the defect up and down in that picture? Push it all the way up to infinity and say that I'm in ZD, and then bring it all the way down to B and say that I'm in ZD prime?
Yeah, you can do that, or you don't have to move it. You're already on ZD here in this space here.
So what you're calling flow is just to go up. from
Right.
one
So
region to another?
right, the flow is just you cross this boundary. That's all. That's the flow here. And the way we check that.
The other way, according to you.
Yeah. And so what we do here is actually checking what is the RG flow on the boundary. That's why we have a fusion here. So by construction, where we have this defect that goes between the two theories. But once we check with the boundary degrees of freedom, so we see that indeed it's mapping things in the appropriate way. Yeah, but just now, once we have that, we know that this is it. This is it. Like you go from plus epsilon to minus epsilon, you're already like you are past the RG flow. You're like in the other end point now. Yeah.
Why is it clear that G prime is less than D? I'm sorry, bigger than?
We build them that way, so that because these guys like to flow to decrease the size of the corner. So we're taking here, let's say we're taking this will be bigger, this D will be bigger than D prime here.
D should be bigger than G prime.
Yeah.
Yes, I agree.
Yeah.
Basically, T is the number of operators you have, some primary type operators you have.
That's, why do you say that?
Well, because you're gonna basically say that all my spectrum is related to, you know, if I have some free field, and then I have free field to, how do I say it? When you say that your superpotential is 0, but you're doing the Landau-Ginsburg model of ZD.
Correct.
You're actually projecting on some ground states, right? You're projecting out the ground states that are not ZD invariant.
Yeah, the twist fields, I'm not sure where they show up in this discussion that we have here. They show up here, for example, these guys, but not in the defect. When we're talking about these guys here, these are actually this corresponds to every sector, every twisted sector, every xj. But in this language here, I'm not sure where those things are. I don't think we see them here. Like, I don't think they show up here. We can build.
I guess I'm just asking what you said all the right things, right? Because you said that okay, so first of all, you're doing Archie flow. So the theory on the left should have more degrees of freedom than the theory on the right.
Right.
That will be true when D prime is smaller than D.
Yeah. Yeah, right.
And the reason is that the one with CD has more vacua or something than the one with D prime, and D is large. Something like that. There are more twisted sectors and stuff in those theories. I don't know like what that has to do with. But anyway, the point is, it's because I don't know enough about Landau-Ginsburg models, but so you need more states in the left than on the right, otherwise you can't flow anything else.
Yeah, and that's what happens here. We see that we send a 1 to 0, a 1 to the boundary, irreps send to 0, and we keep a smaller set, which label the other group, a small group.
How much of this has been free phrased in terms of just abstract algebra? Because it sounds like almost everything you said can be in the matrix factorization part can be said in specific terms.
It's very much. It gets very deep very quickly into homological algebra. And, the theorems that I claim that we use, just the results, they are very abstract.
By who do you know?
A lot of mathematicians. I have the papers. I can be interested. So it's cool because then the question. So defects are very rare. Actually, like only the free boson C1 theory has been cataloged all these defects. So most of them, only that theory.
What's the free boson?
Like the free compact boson.
C mod D.
No, C equals 1. The central charge equals 1. CFT, the bosonic boson. It's the only one that people have looked at all these defects. So the cool thing about matrix factorization is that you can write arbitrary defects. You just write some factorization over some matrices of W, and you have a defect. Now the question is the other way around. If you want some useful defect, then you have to have a matrix factorization that does something important, and that means factorizing a polynomial, which generally is a very tough question. Like that's a research area in math, like how do you factor polynomials?
We don't even have to factor in interest, so.
Over and over, yeah.
Oh, actually, I'll let this make.
So it's bittersweet. It's a bittersweet tool.
Why?
Oh,
Basically, like up to some equivalence, every matrix factorization will give you a defect, right?
Yeah, that's right.
So, and you can just figure out what the degrees of freedom on this thing are. Yeah.
But that's right. But the hard question is the other way around. So right, any matrix factorization will give you a defect. If you find a defect that will do something and you want to do this matrix factorization, then
So matrix factorization.
that would be, because for the same defect, from the same two theories, you can write different defects. It's the ones that will do something for you are the ones that are hard to find in this language.
We will do something for you.
Yeah, like for example, that the defect that PM that will change your label from 2M to 20 plus M mod CD, for example. If this is the rep label, finding defects that do things, useful things. So finding matrix factorization that would enforce things that are useful.
Is that one not useful? What's the problem with that one?
This one here? Wait.
The only one you wrote.
Well, that was the boundary condition, and it was like the rank 1 matrix factorization, which out of it you can build or the other ones. But by itself, it doesn't do anything. It's just a building block, the little one. Just look at this.
I guess I don't really understand because your seemingly only condition is about some theory that kind of looks like a Landau-Ginsburg theory that has a specific superpotential that you can compute that just from the differences of two superpotentials, and that thing lives on the defect. So how does that?
What leaves on the defect? What is that leaves on the defect?
I don't know, your pulled back theory with your W, X, and Y superpotential. You wrote a W of X and Y, and I
Right.
think there was some confusion about what that meant, because
Yes,
W of X and W of Y are living in different places.
Correct.
And then the statement was, oh, this is on the defect, right? So I'm assuming you have in mind the induced theory on the defect with that specific superpotential.
Right, in that case, the condition would be that W1 minus W2 can be factorized with the superpotentials of the theory that you put living on the defect. The same way we wrote W equals J, E, summing. That's the only thing that would be satisfied just on the defect. That's it.
Right, doesn't that tell you about the theory on the defect?
I guess, but we don't really, we really haven't looked at the theory that lives on the defect.
If you have the factorization, though, you can extract the J's and the E's, right? And doesn't that determine the theory on the defect? Or can you not get the J's and the E's? The J's and the E's are what determine the theory, right? The action of the defect action, or the.
Yes. Yeah.
Everything you wrote is very explicit.
But like
In
this,
fact, it's probably too explicit, right?
But this whole example is just for zero superpotential, right?
Yeah, okay, that's true, for that example, yeah.
So he's like saying we try to set all this up now where theory 1 and